All right, so time for what we really came to do. We took a look at sequences, that's nice, but we really want to look at series, which is a part of how calculus works. So I want to talk about what a series is. I want to talk about how to decide whether or not one converges. That's my plan for the next 10 or 12 minutes. So, by definition, an infinite series. Now, you'll remember this notation from high school. This is the sigma notation. This is a Greek letter that makes the S sound. It means sum from 1 to infinity of some sequence a sub n. This infinite series converges to some number s if its partial sums converge to s. That is to say, if the limit as n goes to infinity of the partial sums is s, where s sub n is a1 plus a2 plus all the way up to an, then we say that the sum, as n goes from 1 to infinity, of a sub n is also s. Wow, that just, you ought to read that. You ought to probably read that twice. Just saying. Just saying. Okay, so we should probably talk about what happens now. The easiest series that we talk about. The easiest series that we talk about, and we do this for like not very long, is the geometric series. This is the most interesting series that you looked at in high school. The geometric series is the series where you start with A, and then you add AR, and then you add AR squared, and so on. That's a geometric series. You have some number, you multiply it by R, you multiply that by R, you multiply that by R, and you add them all up. So that the nth term is A times R to the n minus 1, and so on. This you remember from high school. Someone has proven these results to you, I trust. And those results are as follows. If the absolute value of the common ratio is less than 1, then the sum of the infinite geometric series is first term over 1 minus r. This is standard high school mathematics in New York right now. If the absolute value of r is greater than or equal to 1, then the summation diverges. This is basic stuff. So, consider the following. Bill Nye the Science Guy. So we've got 1/9 plus 1/27 plus 1/81 plus and so on. It's a geometric series because the common ratio is 1/3 every time. We're multiplying by 1/3, we're multiplying by 1/3, and so on. 1/3 has an absolute value less than 1, and so its sum is first term over 1 minus r. And that happens to be 1/6. Now, I'm going to go back to the thought on 2 slides ago. I'm going to go back to that thought. What does that mean? That means if I take a look, oh, let's bring in screen shade. Yes, great. That means if I take this sum and then this one and then this one, and I keep going, and I keep plotting those partial sums, 1/9, 4/27, whatever comes next, and so on. If I plot those sums get closer and closer to 1/6. None of those sums is 1/6, but all of those sums are getting closer to 1/6 as n gets bigger and bigger. Okay? Similarly, 3 minus 3/4 plus 3/16 minus 3/64 plus, and so on. You've got a common ratio of -1/4 every time. Multiply by -1/4, multiply by -1/4, and so on. So this is a geometric series whose sum is first term over 1 minus r. And that happens to be 12/5. None of the partial sums are 12/5. But if I plot 3, 2 1/4, then this sum, and so on, those sums all get closer to 12/5. Okay? I'll leave you to think about this one. What about the sum as n goes from 1 to infinity of 2 plus 3 to the n over 5 to the n? And you can think about that in a bunch of ways. You can write out some stuff, and that would be fine. We can talk about that when we gather. Okay, simple application, and then we're done. A simple application. Let's express 0.353535 dot 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 as a simplified fraction. Well, this is a super neat question because it makes us recognize that this is a geometric series. It is a geometric series where we're going to look at things in blocks of 2. See, this 35 represents 35/100ths if my place value from elementary school is accurate. And this 35 represents 35 over 10,000, tenths, hundredths, thousands, 10,000s, 10,000s. And this 35, tenths, hundreds, thousands, 10,000s, 100,000s, millions. This is a geometric series. This geometric series has a common ratio of 1 over 100, and that has an absolute value less than 1. So that is first term over 1 minus r, and that happens to be 35 over 99. I can express an infinite series as a simplified fraction. The thing we should talk about when we gather is this. That we should talk about when we gather. And that's coming sooner than you think. So I look forward to talking with you about some big ideas when we gather to, no, I have more. I'm so sorry. I have more. I have more. Oh man, now you hate me. I'm going to get all sorts of comments about how I thought this was over and it's not. 2 other thoughts before we're done. One is a thought about telescoping series. What if I want to find a sum of 1 over n times n plus 2? Well, if I want to find the sum of 1 over n times n plus 2, that becomes tricky because if you just write out some terms, there's no really immediately discernible pattern. I can't really do a heck of a lot with that. But I think to myself, I'm a Calc 2 student. This is a factorable denominator. And this denominator The fact that it factors makes me think that I can rewrite this. And that would be a wonderful thing to do. So if you were to go through the whole business of partial fraction decomposition, you would figure out that this sum is 1 over 2n minus 1 over 2 times n plus 2. Now you start writing out some terms. We'll pull out the 1/2. You start writing out some terms, and you get 1 over 1 minus 1 over 3. And then if n is 2, you get 1 over 2 minus 1 over 4. And then if n is 3, you get 1 over 3 minus 1 over 5. And then if n is 4, you get 1 over 4 minus 1 over 6, and so on. To which you say, so what, Rooter? So what? Well, they go away, and they go away. And in fact, we know that this negative 1/5 is going to cancel out with one of those jobbies. And this negative 1/6 is going to cross out with one of those jobbies. And what is left? Those are left. And so this thing turns out to be 3/4. Partial fraction decomposition becomes a way for us to evaluate an infinite sum where there's no real pattern up here to look at. If you're interested in trying it out, you might want to prove that the sum of the 1 over 4n squared minus 1's is a half. I'll let you figure that out. But I really want to keep this under 15 minutes, and I have one more thing to talk about. Let's talk about the nth term test for divergence. The nth term test for divergence says that the series sum of the a sub n's will diverge if the limit of the terms themselves is anything other than 0. That is to say, if you take a look at the terms themselves and you find out that the terms are not going to 0, then adding up a whole bunch of things that aren't 0 blows up. If I add up a whole bunch of things that aren't 0, blows up. So, for example, I look at this series and I think this goes to 1 as n gets large. So I'm adding up infinitely many things, and eventually they're all 1 plus 1 plus 1 plus 1 plus 1. This series diverges. Whereas, I don't know about this one, and I don't know about this one, and I don't know about this one. But we can talk about those when we gather. See if this test applies to any of these. Maybe it does. All right, I've out under 15 and that's it. I'll see you then. Bye.